The electric force from the electric field will push a charged particle. Talking about charged particles, what do I mean? I can mean you either have a negative charge, such as an electron, or you can have a positive charge, such as a proton. But every single charge has something that's associated with it, which is the electric field. In negative charges, such as the electron, the electric field is pointing in towards the negative charge, attracting things. Whereas in positive charges, or the proton, things are being pushed away. The electric field lines are going away from the positive charge. This causes, when we see positive and negative charges, this is what attracts them. And when we have the same charges, such as a negative and a negative, or a positive and a positive, they repel each other. So now that we know negative particles are attracted to positive particles and vice versa, we can look how these particles are in a uniform field, electric field. Knowing that opposite charges attract and like charges repel, we can see that the electron in this uniform electric field will be attracted to the opposite way of the electric field towards the positive plate. Whereas the proton, having a positive charge, will go and be attracted in the same way as the same direction as the uniform electric field. These directions and attraction is called the electric force.
So to understand the motion of charged particles or even neutral particles inside an electric field, specifically a uniform electric field, you must understand what a uniform electric field is. So a uniform electric field means that all of the electric field lines are going in the same direction. Lastly, to understand the motion and trajectory of these particles inside of the uniform electric field, one must first understand these three kinematic equations. So the kinematic equations essentially are relationships between the velocity, which is essentially the speed of the particles, as well as how much they move, how fast they accelerate, and how long it takes them to do all of these things. All of these variables can be represented by Vf, which represents the final velocity of the particle, Vo, which represents the initial velocity of the particle, A, which represents the acceleration, so how fast it speeds up or slows down the particle, and delta D represents the actual displacement, so the distance it traveled. We're going to explain how you can calculate all the factors that go into a charged particle moving through an electric field. In that case, it would be its velocity, its displacement, and all of those things. So in this example, we have a negative charge, an electron, moving through an electric field which points in the negative y direction at a velocity v at a 30-degree angle to the x-axis. So before I explain anything, you have to understand that motion of almost anything occurs in two planes in this case, the x and the y plane. The x plane is the horizontal plane, and the y plane is the vertical plane. So the first thing you must do with this knowledge of the velocity is break this velocity into its components, being the x velocity and the y velocity. And to find Vy, essentially you have to understand that sine of theta will equal the opposite over the hypotenuse. So in this case, sine of theta, theta being 30 degrees, would equal your velocity in the y direction over your velocity, the magnitude of your velocity. And to find the x in the x direction, in our little triangle here, it would be, you have to understand that cos of theta equals the adjacent over the hypotenuse. So in this case, it would be Vx over V, and in this case, Vx would equal cos of theta, maybe 30 times the magnitude of the velocity. Now for the actual calculations. So, like I said before, all of this occurs in two planes. So for that reason, we must divide our calculations into the two planes as well. The x plane and the y plane. E perpendicular essentially means that we're relating the events that occur perpendicular to the electric field. And E parallel essentially means relating elements that occur parallel, so in the same direction as the electric field. Start off in the x direction, perpendicular. The forces, the electric force in particular, acting on the charged particle in the x direction, well, there is none, because the electrical force is actually pushing down in the negative y direction. So for that reason, Fx, or F perpendicular, is 0. It's the same case for the acceleration. The acceleration occurs only in the y plane. For that reason, acceleration in the x plane is 0. Next is our velocity. Velocity in the x plane is constant. It doesn't change in this case. So, for that reason, it remains constant. V perpendicular will equal Vx, which we did designate as cos of theta times the magnitude of the velocity. Lastly, we can determine our displacement in the x direction, being delta x, knowing that since our velocity is constant, we can use this equation, being v equals the displacement over time. If we rearrange this equation, we get the displacement in the x direction equals our x velocity times the time. Now for the y direction, therefore parallel to the electric field. the force, the electron force, is acting in this direction. And to calculate it, you have to understand that the electric field inside of it can be calculated using the net force acting on that charge divided by the charge itself. So if you rearrange that equation, you can get that the force will equal the electric field times the charge of the particle. So this is how you would calculate the force acting on the particle. Next, you have to calculate acceleration. We know from our previous physics classes that the force on anything will equal the mass times the acceleration of something. So if you rearrange that equation, you can get acceleration would equal force over mass. Knowing that force is equal to E times Q, we can simply replace that in this equation to get our acceleration is E times Q over m. Next, the displacement in the y direction. So how much it moved on a vertical plane. We can use our trusty kinematic equations, all right? So depending on the information that we're given, this one we decided to use this equation where delta y equals the initial velocity times the time plus half times the acceleration times the time squared. We know that this portion here is going to equal 0 because there is no velocity acting initially in the y direction, and all is going to occur at the end.
All right, here's an example to help you guys figure the concept out. Here we have a uniform electric field with a magnitude of 10,000 newtons per coulombs, represented in this diagram. If an electron is released from the rest of the upper plate, what is the acceleration? What is the final velocity? And how much time did it take to travel between the plates? So this diagram shows the electron moving downwards from the negative plate to the positive plate, and the electric field is going upwards. What we know is the charge of the electron, the mass of the electron, the electric field magnitude, and the delta y distance. So the values we have in the electric field in the x direction are all zeros. The force perpendicular to it is 0, acceleration is 0, but the end of velocity in the x direction is 0, which means that the particle would be moving downwards, accelerating downwards. The delta x is 0 because it's only moving in the delta y direction. Here's the first equation that we need to remember from the previous explanations. And there's the equation of the acceleration of F over m. The F will be replaced with this one, and we simply plug in the values to get the acceleration value, which is this. Now to find the final velocity, we're going to use the kinematic equation, this one, where the final velocity squared equals velocity initial squared plus 2 times acceleration times the delta y. In this situation, the initial velocity is 0, so we just cross it off. And then, simple stuff, we just plug in the values we have, and we got our final velocity. Final question is the time that it took to travel between the plates. We use the other kinematic equation that we have that has the time in it. The initial velocity is also 0, and we plug in the values, isolate t, and we got this.
Well, we want to know, how does this apply to the everyday person? All those people who really aren't scientists, but that this concept applies to. One of the best ways I can think of is Millikan's oil burning experiment. Millikan took a can, and he attached a positive and a negative plate to it. He also attached an atomizer that he filled with oil. The atomizer, as you pump it, produces single particles of oil, negatively charged particles of oil, and it sprays into the can. As he raises and lowers the charges of the plates, Millikan was able to get the particles to float in the center of the electric field created by the two plates. Using the concept we have been discussing, he was able to find out that the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. Thanks for watching.